I discussed the general concept of higher form symmetries. And in today's lecture, I want to talk about this one form center symmetry. So this is a particular example of higher form symmetry, but this is the most important example because this exists in gauge theories, and this concept is directly related to the concept of confinement. So let me start discussing this one form center symmetry. And I start from discussing U1 gauge theory. I discuss it because, first of all, this is very simple. In particular, I start from just the free Maxwell theory. That is very simple. And we can discuss one form symmetries very explicitly. And also, this case of U1 gauge theory is relevant for non-abelian gauge theories. Because, so let me make a remark. So if we consider any non-abelian gauge group G, then this D group contains Cartan subalgebra. Cartan subalgebra is some product of U1 groups. U1 to R inside this group G. And here, this R is the rank. So I think this is familiar from learning from some real algebra. So for example, this is explained in the book of Georgia about real algebra or something. So, and some properties of this non-abelian gauge group is contained in this Cartan subalgebra. So if we understand this U1 case well enough, then we can also understand the non-abelian gauge groups. So this is the reason that I discuss this U1 case in detail. And in today's lecture, I just discussed the case of 4 dimensions. But it is very easy to generalize it to other dimensions, such as 3 dimensions. So there are many people studying 3-dimensional gauge theories, and they extensively use this concept of one form center symmetry and its generalizations. Because in 3 dimensions, there is no perturbative anomaly, so we have to use some global anomaly in 3 dimensions. Then one form center symmetry is really very important in the study of 3 dimensions. But in today's lecture, I just focus on the 4-dimensional gauge theories. Okay, so let's start. So I just consider free Maxwell theory. The Lagrangian is very simple. It's just 1 over 2g squared f which star f. This is very simple. And for simplicity, I just set the theta angle to 0. And here f is just the field strength, the exterior derivative of U1 gauge field. So this is very simple. Then in this system, there exist 2 one-form symmetries. And we can explicitly write down the conserved current in this free Maxwell theory. So there is electric one-form symmetry. the conserved current of this electric one-home symmetry, or more precisely, its Hodge dual, is given by some factor times the Hodge dual of field strength. Here I put this factor 1 over g squared, the coupling, just for the convenience. The reason that I put this will be clear in a moment. And another symmetry is magnetic one-home symmetry. The conserved current for the magnetic one-home symmetry is given by 1 over 2 pi times F. So for electric one-home symmetry, we take the Hodge dual, and for the magnetic one-home symmetry, we don't take the Hodge dual. The F itself comes here. And they are conserved because the conservation equation is just free Maxwell theory. So free Maxwell equation is just in the language of differential form. It is just given by the exterior derivative of this Hodge dual of electric current is 0, and also the magnetic current is 0. This second equation is just the Bianchi identity, and this first equation is usual Maxwell equation. So in free Maxwell field theory, we can explicitly see that these currents are conserved. So therefore, we have one-home symmetry. And this is one-home symmetry because these currents are two forms. They are two forms. So it is very easy to see the existence of one-home symmetries in these Maxwell field theories. And because there exist these one-home symmetries, we can also construct symmetry operator and in particular, for later purpose of generalizing to non-abelian gauge groups, I want to slightly rewrite the electric one-home center symmetry. The electric, okay, so I slightly rewrite the electric one-home symmetry. So first of all, as I discussed yesterday, we take some two-dimensional surface. Then we can define the symmetry operator U as the exponential of the integral of the current over the surface in this way. Then let's put this operator in the path integral. So in the path integral, action is given as follows. So first of all, we have just the free kinetic term for the Maxwell field, which I write before. And this is integrated over the entire space-time. This M is entire space-time. And if we insert this symmetry operator, then because this is exponential of something, in the path integral, we can put this exponent in the action. So we can write it as like this. So we have an integral of the electric current over this surface. And electric current was given by 1 over g squared times h dual of the field strength. So this is the action in the presence of the electric symmetry operator. Now this first term is just quadratic in the field strength, and this second term is just linear. So we can complete the square. For this purpose, we can rewrite this term as integral over the entire space-time of h dual of f. Delta function on sigma times h dual of f. This delta sigma is delta function. Then we just complete the square, and that's very easy. And the result is just like this. So if we complete the square, so it looks almost the same as free Maxwell kinetic term, just like this, up to some background field. So there is some term which is purely background. But here, this is f prime, sorry. Here this f prime is defined as the original f plus, sorry, I forgot to put the parameter alpha here. Yes, this symmetry operator depends on this parameter alpha. So we multiply this charge by some parameter alpha and then take exponential. And the parameter alpha comes here and here. So this f prime is this alpha times the delta function localized on the surface sigma. Then from this f prime, we define new gauge field A prime such that the exterior derivative of A prime is f prime. So we just change the variable of gauge field from the original gauge field A to this new gauge field A prime. And the reason that I put the factor of 1 over g squared here in the definition of electric current is because if we put that factor, then I don't have any factor of g squared here. Okay, so we define this A prime new gauge field. Then this gauge field has a non-trivial holonomy around the two-dimensional surface. So if we integrate this A prime around sigma, then this holonomy is alpha. So this sigma is actually a two-dimensional surface, but for simplicity, because this whiteboard is two-dimensional, let's write it as a point in this whiteboard. Then we take a small circle around this sigma and compute the holonomy around this sigma. Then this holonomy of the new gauge field A prime is given precisely by this alpha, parameter alpha. So in this way, we can rewrite the electric symmetry operator as a kind of singularity around this sigma. And this definition is more convenient for the generalization to non-abelian gauge group. Because in the case of non-abelian gauge group, I just erased it, but in the free Maxwell theory, we had the explicit current operator, conserved current operator. However, in the non-abelian case, we don't have any explicit conserved current. But this definition, by using the holonomy around this sigma, this is applicable to non-abelian gauge theories as well. So the insertion of this, this is electric symmetry, electric one-form symmetry. Yes. So insertion of this electric one-form symmetry operator corresponds to holonomy. Holonomy around this two-dimensional surface sigma. And originally such an operator defined as a singularity around sigma by this holonomy. Such an operator was discussed by Gukov-Witten. So this holonomy around sigma is discussed by Gukov-Witten, and this is called the Gukov-Witten operator. So Gukov-Witten discussed this even in the absence of any one-form symmetries. So this definition, holonomy around sigma, this can be defined even if there is no symmetry at all. However, in special cases, this operator is invariant under continuous deformation of this two-dimensional surface. And if this operator is invariant under this continuous deformation of this surface, then that means that this operator defines some symmetry. So one-form symmetry, electric one-form symmetry operator is a special case of Gukov-Witten operator in which this operator is kind of topological. Yes.
Can you be more explicit for the case of a Maxwell theory? For example, what kind of a source? What kind of a source?
Source?
Source, electric charge or magnetic charge, or what kind of a source can generate such? I mean, for example.
Here I'm considering just a free Maxwell theory.
Yes.
But in the path integral, I just put a singularity of Maxwell, free Maxwell field around this sigma.
I don't understand. What do you mean? I mean, how Maxwell? I mean, free Maxwell theory can have a, singularity.
So usually in the path integral, we just integrate over smooth gauge fields on the space-time manifold. But instead of smooth gauge fields, I'm just considering the path integral over some singular gauge field. This is singular around this two-dimensional surface. And singularity is, so if I denote the angle by theta, then singularity is specified like this.
But I think that any field configurations of singularity should be generated by some kind of a source, right?
No, I'm just putting the singularities. There's no source.
So what are you doing then?
I'm just doing path integral over gauge fields which has this kind of singularity. That's the definition.
So here you inserted a fundamental effect.
Yes.
And that is not the usual, I guess, a source.
Okay. But maybe I should mention that this Gukov-Witten operator has many more applications, more than one-form center symmetry. For example, it is very important in the study of some supersymmetric gauge theories, which is obtained by compactification of some six-dimensional gauge theories called class S theories. So maybe maybe it's useful to remember the definition of Gukov-Witten operator.
An explicit example where the operator depends upon on sigma, like we're trying to differentiate if it depends upon sigma or is independent topologically under deformations of sigma, then it's a symmetry operator or not, right? Mm-hmm. So do you have an explicit example where it depends upon sigma?
That depends on sigma.
Yeah.
If we introduce some charged particles, then it's not topological anymore. Because if we introduce charged particles, then the conservation equation is violated. I will discuss that later. Then it's not topological anymore.
Excuse me. Hello.
Yes.
Yeah. So is it f prime an exact differential? Is it guaranteed that we can always find an a prime such that the dA prime equal to f prime? Or in other words, is f prime guaranteed to be an exact differential? F prime that you have written, is it guaranteed to be an exact differential?
F prime is okay. So let me say I started from explicit current, but I can define the operator just by this singularity. So we can regard this just as a definition of the symmetry operator U. Does this answer your question?
I think he's asking if it's always possible to write F prime as an exterior derivative. So in that sense, F is always exact. F prime is always exact.
Yeah, I mean, outside of this singularity, it's just a free Maxwell theory.
Right. So
outside of this singularity, it satisfies the standard Bianchi identity. So yes, so as usual, it is possible to find this.
okay, thank you.
Okay, so let me also mention about. Sorry. No. Now I discuss operators which are charged under these symmetries. The operator which is charged under the electric one-form center symmetry is a Wilson loop operator. Wilson loop operator which is just defined as follows. So Wilson loop operator depends on some loop, and I denote the loop by this C. Then it is an exponential of the gauge field around C. So this was Wilson loop operator. By the way, sorry. From now on, I just drop this prime. So everything I will say is about a prime in the previous notation, but I just drop this prime for simplicity. The reason that the Wilson loop operator is charged under the electric one-form center symmetry is very clear from the definition of the Gokov-Witten operator. Because if we cross the Wilson loop and Gokov-Witten operator, then if we cross this Wilson loop and Gokov-Witten, suppose this curve is C, and suppose we have Gokov-Witten operator here, and then if we cross it, so if we slightly deform the curve and then we cross this operator, then by definition of the Gokov-Witten operator, we pick up a holonomy around this sigma. So by crossing these two operators, this Wilson loop gets a phase factor exponential I alpha. This just follows from the definition of Witten. So, and this phase factor means that the Wilson loop operator is charged under the electric one-form center symmetry. So let me write it explicitly. So this W, this Wilson loop operator has a charge. Charge 1 under electric operator. And let me also mention the case of magnetic symmetry. The magnetic, so the operator which has charge under the magnetic one-form symmetry is a two-fifth operator. So that's easy to guess because of the electric magnetic duality. So two-fifth operator, which I denote as Hc. This has charge 1 under magnetic symmetry. This is also easy to see from the definition of the two-fifth operator. Two-fifth operator is defined as a singularity around which there is some magnetic current, magnetic flux of gauge field. So suppose that there is two-fifth operator here. Then its definition is that there is magnetic flux from this two-fifth operator. So this position of the two-fifth operator is again a singularity of gauge field configuration. And this is defined in such a way that if we integrate the gauge field divided by 2 pi around this around the position of two-fifth operator, then this is equal to 1. So this is the definition of two-fifth operator. However, this f over 2 pi, this was just the Hodge dual of the magnetic symmetry current. So this equation means that the two-fifth operator is charged under the magnetic symmetry. And here I discussed it for the case of 4 space-time dimensions. But this is more famous in the case of 3 space-time dimensions. So, because this is very extensively used in the literature, let me just make a comment about 3 dimensions. Well, more generally, in these space-time dimensions, magnetic symmetry this magnetic symmetry is a D minus 3 form symmetry. this d minus 3 can be seen just from counting the degree of this form. So this f is a 2 form. So if we take the Hodge dual, then it is d minus 2 form. And that means that this magnetic symmetry is a d minus 3 form symmetry. And in particular, if d equals 3, then the 2-Hooft operator is called monopole operator in the special case of d equals 3. Sorry, this H is called, because in 3 dimensions, this is just 0 form symmetry. So this is just the usual symmetry. And the usual symmetry acts on usual operator, local operator. So 2-Hooft operator is defined just on a point. And in this case, so in 3 dimensions, this is called monopole operator. And the symmetry is what is called topological symmetry.
Question?
Yes.
Is the monopole you mentioned in 3 dimensions is the same as the monopole we are talking about in compact QED in 3 dimensions? They are same thing.
Sorry, what?
In 3-dimensional compact QED, there's monopoles.
Compact 3D?
3-dimensional compact QED.
QED. Yes.
And so, are they same thing?
Yes. I'm here discussing just free Maxwell field theory. And in 3 dimensions, that is also there to compact scalar field. Is that what you are mentioning? So this is, yeah, in 3 dimensions, this is exactly.
Okay.
Yeah.
I see.
So U1 gauge theory in 3 dimensions has the monopole operator and topological symmetry. And this is really very important in the study of 3-dimensional gauge theories. In my lecture, I don't use this case of 3 dimensions, but it is a very important concept. And up to now, I have just discussed the free Maxwell theory. And free Maxwell theory is too simple. Usually, we want to consider some interacting field theory. Then, these electric and magnetic symmetries are explicitly broken. The reason that they are explicitly broken is very simple, because I mentioned that the conservation equation of electric current, electric one-form symmetry current and magnetic one-form symmetry current is just the free Maxwell fields, free Maxwell equations. But if we introduce charged particles, then the exterior derivative of these currents are no longer zero. We have non-zero contributions. Here, this small j is just the usual electric current. For example, this is produced by electrons, muons, and so on. And this small jm sorry. My writing is very bad. This small j, this is capital J, and this is a magnetic current. And this is produced by, for example, magnetic monopoles, which are charged, which has a charge of magnetic ion. So in the presence of the charged particles, these currents are no longer conserved, so these symmetries are broken. But depending on the matter content, some subgroups of electric and magnetic symmetries can be still conserved. So let's suppose the following. So let's assume that all particles has electric charge which is a multiple of n. Here this capital N is some integer, some fixed integer, and suppose that all electric charge is a multiple of this integer n. Suppose that the matter content is like this. Then we can consider a Gukov-Witten operator. With a special parameter. The holonomy, I take the holonomy to be just holonomy to be just 2 pi small n over capital N. So I take this specific holonomy. So this means that I introduce this Gukov-Witten operator such that this holonomy is 2 pi small n over capital N around the surface sigma. Then this Gukov-Witten operator is invisible to all the dynamical particles in the theory because we assumed that the dynamical particles has electric charge which is a multiple of capital N. Then what is relevant for the quantum mechanical action of charged particle is this holonomy. So because dynamical particles has charge E, we multiply by this charged particles charge. Then this holonomy around sigma, this is just 1 because of this condition and this special value of the holonomy. So this means that the singularity is invisible to charged particles. So in this situation, because this singularity is, I have to say, this is locally invisible to, at least locally around this sigma, this is invisible to charged particles, then it is possible to deform this sigma, and there is a topological invariance. So this subgroup of the symmetry is still preserved in this case. So there is an explicit breaking. So originally we have continuous one-form symmetry, continuous U1 one-form symmetry, but it is explicitly broken to Zn subgroup. And here this capital N is specified by this condition. So I assumed that all particles have charges multiple of this capital N. Then the Zn subgroup remains. So this is a typical situation. So because we want to consider some interacting field theory, this U1 symmetry is usually broken. But still we have some discrete subgroups. And we can use these discrete subgroups in the actual applications. Okay, so this is explicit breaking. Let me next discuss spontaneous breaking. Yes.
In this part, if I consider a non-abelian, just pure Yang-Mills, let's say.
Yeah.
Then also I will have some similar breaking of.
Yes. So if we consider, for example, I will discuss this later, but if we consider, for example, let's consider SU2, then it has Cartan U1 subgroup, and W boson has charge 2 under this U1. So that means that there's G2 subgroup, G2 center symmetry subgroup in this SU2 Yang-Mills theory. Yeah. So in non-abelian gauge theory, we just have some discrete center symmetry. Okay, so let me discuss spontaneous breaking. And I mentioned yesterday the condition about spontaneous breaking. So we consider some charged operators and take the size of the operator to be very large. And if the wave vanishes in the limit of very large size, then the symmetry is unbroken. But if the wave of the operator remains non-zero, then the symmetry is broken. So let me write more explicitly. So I consider this Wilson loop and 't-Hooft loop in the limit in which the loop size goes to infinity. Then we can classify phases of gauge theories. So let me write a table. So typically there are three phases. Actually, there are many more phases in general, but typical phases of gauge theory is these three phases. The first one is Coulomb phase. This Coulomb phase is just something like the U1 QED of the standard model. So the massless, just Maxwell, massless spin 1 gauge field remains in the long distance limit. And next phase is a Higgs phase. This is just like the SU2 of the standard model. And finally, we have confinement phase. This is like a SU3 gauge group of the standard model. Then we consider the behavior of Wilson loop and the two-hooft loop. And by looking at the behavior of these operators, we can see whether the electric one-home symmetry and the magnetic one-home symmetry are broken or not. So in the Coulomb phase, this Wilson loop and the two-hooft loop does not show any area law. So up to some renormalization factor of these loop operators, in the Coulomb phase, these operators are both non-zero. So that means that the electric one-home symmetry is broken. And magnetic symmetry is also broken. So this is the situation of Coulomb phase. And in the Higgs phase, this Wilson loop operator is non-zero up to renormalization. It shows something called the perimeter law. But this two-hooft operator goes to 0. And then electric symmetry is broken, and magnetic symmetry is unbroken. And in confinement phase, the Wilson loop operator shows the area law, and so in the limit of large size of the loop, it goes to 0, and the two-hooft operator is non-zero. So the electric one-home symmetry is unbroken. This is preserved. Electric symmetry is preserved, and magnetic symmetry is broken. So this is the situation. Let me write. So let me explain a little bit more. So So the fact that this Wilson loop operator is non-zero in Higgs phase can be very easy to see, because in the Higgs phase the gauge boson becomes massive. So in the ground state, or in the Higgs phase, the gauge field, we can just set the gauge field to be 0 up to gauge transformation. And if the gauge field is 0, then at the classical level, this exponential of integral of gauge field is just equal to 1 at the classical level. And there are quantum corrections, but that is observed by, that is cancelled by some operator renormalization. So basically, this is exponential of this. The integral of A is just equal to 1, which is non-zero. So by this reason, Wilson loop has a wave, and the electric symmetry is broken. And on the other hand, the 2-fifth operator goes to 0 in Higgs phase. So this is known in superconductor. This is called Meissner effect. This really happens in superconductor. And the reason is that the magnetic flux is confined in superconductor. Yeah, I think some of you have seen that if we put superconducting material on magnetic field, then that material is kind of repelled. And that corresponds to confinement of magnetic flux. I don't explain the detail, but this is very well-known phenomenon. For example, this is explained in Weinberg's textbooks, and of course many other condensed matter physics textbooks. So in Higgs phase, we can explicitly see this behavior. And confinement can be considered as an electric magnetic dual of Higgs phase. I think this was proposed very long time ago by Nambu or someone, but at least this was realized very explicitly in Seiberg-Witten theory. Seiberg-Witten shows that confinement in some supersymmetric gauge theory is really realized as a Higgsing of magnetic gauge field. So now I think this is very reliable statement. The confinement is an electric magnetic dual of Higgs phase. 't Hooft. Okay, thank you. Okay, so this was discussed by 't Hooft. Thank you very much. So the important point is that in this way, we can distinguish these various phases of gauge theories, like Coulomb, Higgs, and confinement phases, by looking at the behavior of this electric one-home symmetry and magnetic one-home symmetry. So, Coulomb phase can be characterized by the statement that electric and magnetic symmetries are broken. Higgs phase is characterized by statement that electric is broken, magnetic is unbroken, and confinement phase is characterized in the similar way. So these symmetries can be used as a characterization of these important phases in gauge theories. And this is really, for example, there are some theories in which electric or magnetic center symmetry does not exist. Then, in such a theory, actually, we cannot distinguish Higgs phase and confinement phase. So if there is no electric symmetry or magnetic symmetry, then Higgs phase and confinement phase can be smoothly connected without any phase transition. So in such a case, we cannot distinguish them. So these electric and magnetic symmetries these are the most important symmetries to distinguish the phases. So this is the main motivation to consider these electric and magnetic center symmetries. Okay, so now I discussed the U1 gauge theory enough. So let me now go to the case of non-abelian Yamil's theories. So I consider one-form center symmetry in Yamil's theory. So let me first start from the comment about SU2 gauge theory. This SU2 gauge theory has U1 Cartan subgroup. This is Cartan. And then we can consider the electric and magnetic charges of this Cartan U1 subalgebra. So I denote the electric charge by E and magnetic charge by M. Then under this Cartan subalgebra, the electric and magnetic charge of W boson. So suppose that, for simplicity, suppose that there exists some scalar field in the adjoint representation of SU2, then by giving a wave to the adjoint scalar field, we can go to the U1 gauge theory by fixing the SU2 to U1, and then there is W bosons and also magnetic monopoles. So we have W boson and magnetic monopole. Then this W boson, so if you very carefully study the normalization of U1 gauge field, then it turns out that the W boson has electric charge 2. And of course, it has magnetic charge 0. And also, monopole has electric charge 0 and magnetic charge 1. Now, the point is that here, the W boson charge is a multiple of 2. And it turns out that all other particles has electric charges which are multiple of 2. So because of this, this U1 symmetry in the low energy has electric Z2 one-form center symmetry. So at least this is the situation in the low energy limit after spontaneous breaking of SU2 to U1. And it turns out that this Z2 symmetry exists also in the UB theory, the full SU2 gauge theory. So let's consider more generally the SUN gauge theory. SUN, gauge group is SUN. Then the definition of one form Zn center symmetry is the following. Here, this n is the same n as here, SUN. The one-form center symmetry can be defined by a Cook-Witten operator. Such that the holonomy around the singularity is given by the center of the gauge group. Okay, this IN is a unit matrix. So this element is a center of the gauge group. And here this small n takes values in this Zn. So this is Zn symmetry. And this symmetry exists if the center acts trivially on all the dynamical fields. The example is pure Yang-Mills theory and also super Yang-Mills theory. So in super Yang-Mills theory, all fields transform in the adjoint representation of the gauge field, gauge group. And in the adjoint representation, the center acts trivially to the matter. So in such a case, this Gukok-Witten singularity is not visible to the matters. Then this Gukok-Witten operator is topological. It is invariant under the deformation of the surface sigma. And so this defines the symmetry. But on the other hand, if there is some fundamental coax, then this center acts non-trivially on fundamental coax. And in that case, there is no center symmetry. So this center symmetry is completely broken if there is fundamental coax. But even if there is fundamental coax, there still exists some variants of center symmetry. And if there is time, I will discuss such a variant of center symmetry which exists even in the presence of fundamental coax. But in most of the lectures, I will focus on the case in which the center acts trivially to all the matter fields. Then this one form Zn symmetry exists. Yes?
If you want to say that it's acting on trivially, you should give the definition of the action, right?
I mean, so what I mean is that if we have a group element of this SUN, then if we have some field, then this group element acts by some representation of SUN, and this is representation of SUN. And in the case of adjoint representation, if we put this center element into this element G, then it is just trivial.
Then how it is acting on the fundamental, for example?
How?
Fundamental representation. If phi is fundamental, then how it acts?
If this phi is fundamental, then this just acts by
just
this
multiplication
factor. So so let me. Let me write here. So if matter is in the fundamental representation, first of all, let me write this center element. C, then this action is just the multiplication by this phase factor. It is just a defining representation. And for the adjoint representation, if we represent the fields in the adjoint representation as if we represent the fields in the adjoint representation as a matrix, n times n matrix, then it acts as G phi G inverse. This is C. And if we take the center element of the gauge group, then we have C phi C inverse, but this C is proportional to the unit matrix. So this C and phi just commute, so this is just phi. So this is the meaning that this center acts trivially on adjoint representation. Oh, 2 minutes. Should I take some questions? Or, I mean, should I stop here? Maybe. Yeah, I think I stop here.
So you mentioned that so the expectation value of Wilson loop or Tooth loop acts like an order parameter, and as you increase the size of the of those line operators, it goes to 0 or become finite. But can you elaborate on that? Like, because naively, as you increase the size of whether it obeys parameter law or area law, it will just it will still stay finite. So I need more justification, maybe.
Sorry, maybe I don't understand. So if we increase the size of C, then if, for example, if Wilson loop shows the area law, then it's exponential of minus area. So if area goes to infinity, then it goes to 0.
Yeah, but also even for the parameter law, if the size increases, it goes to 0.
In the case of perimeter law, I mean, that's the reason that I'm mentioning about denormalization. So this perimeter law is changed if we change how we denormalize the operator. So what I mean is that if the operator goes to 0, regardless of what denormalization we use, then symmetry is unbroken. But if the operator goes to non-zero for some denormalization, then we regard the symmetry is not broken. Broken. Yeah, it's very confusing. Sorry.
Question. Can we add theta terms to your arguments? Here you're talking about pure Yang-Mills or pure Meissner.
Yeah. We
And
can add theta terms. Yes.
And then how much changes?
Maybe there's no change in what I discussed today. Yeah, even if there's theta term. Yeah, I think I can just repeat the same argument in the presence of the theta term. Yeah.
But for example, there is some kind of dion stuff, right? If you add theta, right?
Dion, yeah, there is dions, yes. Yes, but even if there's dions, I mean, if we normalize electric U1 and magnetic U1 in such a way that all particles has integer charges, then this is completely the same. I mean, it depends on how we normalize U1 and U1 electric and magnetic charges. If we normalize these charges in the physical way, then the electric charge contains theta, so by Witten effect. But if we normalize them by some mathematical way, then electric and magnetic charges are always integers, and electric charges in particular multiple of 2, then there's no change.
if theta angle equals pi, then you may have some charge concatenation symmetry.
Even if, I mean, for arbitrary theta, there exists some normalization of electric and magnetic charges in such a way that these charges are just integer. That statement is true for any theta. And so, in particular, even for theta equal pi, they are normalized as an integer, and they have completely the same charge as, sorry, it is erased, but yeah.
Okay. So, but I will say that maybe at theta angle equals pi, you have some extra symmetries. You have some mixed anomalies. So
If theta is pi, then
you have some extra symmetries. Is that possible?
if theta is pi, then there is some additional symmetries, such as time reversal
Time
symmetry.
reversal,
And
that's
that
right.
is
Yeah.
very,
Time reversal symmetry. Yeah.
that is very important in some discussions. Yes, yes.
I see. Okay.
Mm.